Hello, this is Adnan Hayat from IEEE section, and today we have Dr. Imtiaz Madni from PhD from the UWA presenting us on dynamic power system studies and machine modeling in PSCAD. Dr. Imtiaz Madni has his PhD from University of Western Australia. He has strong practical knowledge in designing, installation, and maintenance of electrical systems. He has been working on asset management, reliability, and operations of electrical system devices and machines throughout their life cycle. He has worked within the power generation, renewable mining, water resources, waste to energy, and heat industry sectors. Dr. Imtiaz has successfully managed and delivered several projects in Western Australia in power generation, distribution, and renewable sectors. He is also very active, involved in community, and also do some guest lecturing at various universities and institutes. I would like to welcome Dr. Imtiaz. Can you please share your slides and start presentation?
Hello, thank you, Dr. Adnan. Hello, everyone. I hope you're doing well, and thank you for having me. Thanks for the introduction. Sounds really good. Somebody talking about you. Yeah, so please excuse me if my video is not very clear. I'm actually using my desktop. I wanted to actually share the PSCAD environment with you guys and show you exactly like what we do and how we model. So I had to use my desktop for that. So the camera quality is unfortunately not as good as the laptops, but hopefully you can see me well. I will share my screen and then we can go ahead. Please let me know if you can see my screen clearly.
Yes, we can. Yeah.
Okay, perfect.
Yeah, if you might do full screen, that would be great.
Yep.
Yeah. Thank you.
Sure.
Yeah, that's perfect. Thank you.
Okay, is it clear? Do you see the full screen?
Yes, it's clear. Yeah.
All right. So the topic I chose today is actually, I wouldn't call myself an expert in the topic because obviously it's a very fast developing field, as you may already know. The power system modeling has been changing as the power systems are changing. Yeah, there's a huge transformation going on in energy sector, so the whole power system domain is actually changing very fast. And similarly, there is dynamic or static steady state modeling techniques. They are also developing, and sometimes it's a bit hard to keep up the pace with what is going on and what are the updates, especially at my age. It's a little bit tricky. So I chose this model, just this topic, because obviously it is relevant, very much relevant to the present technology, and PSCAD especially is becoming very popular in the power system industry because of all this renewable energy generation and distributed energy resources, microgrids. So there's a lot of focus on EMT studies. So EMT stands for the electromagnetic transient studies. AEMO, Australian Energy Market Operator, they have specified the use of PSCAD version 5 for all the compliance studies, especially for dynamic EMT studies, and they want all the models to be developed in PSCAD. And we'll discuss why, because I think it has to do with the features it offers are much more dynamic, and you can visualize the results in real time, which is different from other um, power system software. I'm not saying that the others cannot do it, but PSCAD is a lot more user friendly, I would say. A little bit about myself. I think Dr. Adnan already went through it, so I don't need to go through it. I would like to just say that I've been living in several different countries. Like got my master's from South Korea. I worked there and worked in Japan for some time, and then worked in China for several years. And then I finally came to Australia around 9 years now. Um, I got my PhD, and then since then I've been working in industry. I worked in academia for a while, and then I wanted to have a bit of change. And at that time, there was a lot happening in the industry, so I thought it will be a good time to make a move. And since then, I've been working in industry. I've been lucky to be part of several interesting projects in academia as well as in the industry. Um, so I've learned a lot and played my part in several different projects. So over past 3 to 4 years, I've delivered so many projects in Western Australia. So you can see it worth more than $50 million. We worked with Western Power, Horizon Power, AMO, and AusNet. So been working with several different stakeholders throughout my career in Australia. So agenda today is a little bit introduction to power systems. So the way I prepared the slides is I don't want to go into too much details like fundamentals or the fundamental components of the power system modeling and the PSCAD because then 1 hour is not enough, I think. So I will give you an overview. We will discuss how we can develop a model, a very basic. So I got an example of a PV inverter system from which is also important these days for all these renewable energy systems and grid integration. Uh, Most of the studies we do are for compliance, obviously. So then your inverter model and integration with the grid, and how do you monitor different points? So those are very important. So I don't think we'll need to go through too much about the introduction to power systems. I'll quickly skip through that part, and then we'll go on to PSCAD environment. The importance, we already discussed that it is becoming important because the the power system infrastructure is changing. Conventionally, it used to be very simple and straightforward, but nowadays it is becoming complex. And even with the conventional power systems, we used to have several issues, and we used to do studies with them, but we didn't rely too much on dynamic studies. So there were several issues in the past where we had like large outages, which resulted in billions of dollars of losses. So what is driving all this change is our objective, right? So our objective is definitely not staying big. That's pretty much clear by now. We want to go smaller or decentralize the power systems. So that's where we have a lot of different energy resources coming into play. And as you can see, the whole network is changing with the introduction of these renewable energy sources. And the power uh, flow, as you can see, it used to be just one-sided for conventional power systems, but now we have bidirectional energy flow, and similarly we have bidirectional power controls. So, and it's in a microgrid setting. When you talk about a microgrid, it's not just bidirectional, it's actually multi-dimensional, then where you have a lot of smaller energy sources. And um, obviously, to understand or manage such a system, we need to do some kind of modeling. So that's where PSCAD or similar software, they play a very important role, that they give us an idea about how we can control our system or how we can manage the power flows and power qualities, what different requirements we need to meet in order for the system to sustain. So cost of unreliability is huge. If you consider this event, this particular event, which was a Northeast blackout in US, was like 20 years ago, almost 20 years now. At that time, we didn't have as much reliance on energy sources as we have now. By every passing day, we have more and more reliance on our power systems because energy is becoming a very critical part.
Sorry, there's a problem in the voice. I'm not sure if you can see the chat, but we can't hear you very well. There's a lot of noise.
Dr. Imtiaz.
I'll try to reach him via mobile phone. Please bear with us. We're trying to get in touch with Dr. Imtiaz to see what. I think there is some issue in his network.
Hello? Can you hear me?
Yes, we can hear you okay now.
Okay. Sorry, I don't know what happened. I was speaking, and uh,
So we lost your voice in the previous slide, I think. Previous than this one.
this one.
Yes, this one. Yeah.
Okay. So can you hear me okay now?
Yeah, we can hear you okay. Yeah.
Yeah, sorry about that. Yeah, I was just saying that convention power systems, this is just a pictorial view of the power system we used to have it conventionally. It was relatively simple. It had its own challenges, obviously, but compared to what we have today, it was relatively simple. So we could do just simple modeling, and all of the software, modeling software, were developed according to that. But now we have this goal, right? We want to achieve this kind of power grid in the future, where we have residential solar PVs injecting power into the system all the time. We have wind farms, conventional generation from coal or gas, and then we have several other energy sources, bio generation, hydropower, nuclear, and hydrogen. So, and it is a lot more interactive, and consequently, it becomes much more dynamic. And the dynamic in terms of not just its performance, but also in terms of fault tolerance. It has to be very, very dynamic. So in order to understand our power systems designs, then we uh, have to perform such dynamic studies so that we can uh, understand how the system will behave, and if there are any challenges, then we can overcome them. So basically, how the power system modeling is done, so that's very basic. Like we have generation station, and then we have transmission lines. Mostly we model transmission lines as PI models or PI modules, and then we have the substations and loads. So these are the key components in a power system. And data requirement is different for steady state as compared to dynamic modeling. So for dynamic model, obviously we need the data about the type and the size of generator with all of their controls, because controls are very, very important in terms of dynamic modeling. So we will discuss later on how we apply certain controls to control the power quality, fault tolerances, and reactive power, frequency disturbances. So all of them, they need some kind of control. So these conventional as well as the modern generation sources, they all have some kind of control. So we can use those to model a dynamic system. So that data is important, and the data about the load, obviously, it's not just the power systems are changing. The uh, loads are also changing. That means the nature of the loads is different these days. Obviously, we have a mix of resistive and inductive and reactive loads. So location and specification for distributed control devices. That is also an important data. These days we use a lot of StatComs. So that is obviously very important data for dynamic system modeling, their location and specification, and all other communication controls, like how different energy sources are communicating with each other. How do we monitor certain parameters from another point so that we can control the generation on the other side? So that is also very important for dynamic modeling. And then protection schemes, obviously, they are part of the power system modeling. And so once we do dynamic studies, then obviously we need to validate our models. So then there are certain requirements from AMO or all other standards from NERA, and similarly in other countries, they are other regulatory bodies. They have certain requirements. Once we do our modeling and simulation, we need to validate our models. So steady state analysis is, like I mentioned, is pretty much developed, and most of us, we understand it because we have been using it for so many years, and the system in steady state, mostly the systems are pretty much similar. So we just have to have a generation source and any transmission lines. And as I said, we model these days, we model the transmission lines as a PI modules, and then we have the load parameters and the capacitors or compensators. So this is what we used to do conventionally for conventional power systems, and how we can model generation sources and then the distribution and transmission lines. So dynamic systems, they're also called hybrid dynamical systems, because obviously we have this discrete system and then we have this continuous system. And the more changes, so in dynamic modeling, uh, the biggest challenge is these more changes, I would say, and the disturbances. So these can change the parameters quite quickly. So your model or your system needs to respond to those changes or those disturbances in a certain time. So if you want to achieve stability, so that's where dynamical systems, they become a little bit complicated as compared to the steady state modeling. So a lot more parameters are involved, and obviously you need to have certain controls, and the network needs to communicate between different data points. So it's physics based models of networks and generators and loads. The basic emphasis is on our capturing the switching behavior or saturation, and then also looking at the system behavior. So that is mostly done in time domain, like I said. So time is very critical when we talk about the larger systems. So time evolution is governed by these dynamics modeling systems. So uh, obviously there are some uncertainties and limited data, but the model should be able to uh, produce some kind of system behavior, which can give you an idea how your system will behave over time for a certain disturbance or certain mode change. So both dynamic and steady state are important. It doesn't mean that steady state is not important. Obviously, first goal is to build a static state model, which is also called static model. And that mostly works on equilibrium states, right? So where we have equilibrium solutions, so the trajectory in that case is just equilibrium states. When the system reaches a certain point, then we have what is the power output, what is the voltage, what is the current and frequency. So, but dynamic model, it doesn't just produce the change, but also the path to the change, and also how to control the change or bring the system back to normal. So that's where this dynamic model is different from steady state. So that was a little bit introduction about the dynamic modeling and how it is a little bit more challenging than the steady state. So I will jump on to PSCAD. PSCAD, as I said, it's becoming very popular because of its environment. First of all, I think it is very much user friendly, and secondly, the scope. It covers a wide scope, and you can do pretty much everything in PSCAD, like dynamic modeling for renewable energy sources and microgrids, standalone power systems, off-grid systems, and islanding, anti-islanding, and then you have other factors like transmission lines. So it can do insulation coordination, point on wave analysis, and several other analyses related to the transmission lines. Recently, it has been developed to include a HVDC as well. So these days, everybody's not everybody, but a lot of people are talking about HVDC because it offers many advantages over the AC transmission system we have currently. So yeah, there are some projects going on also in Australia. I think there's one project which is in pipeline at the moment. So it is about a large scale HVDC transmission system. So yeah, this software PSCAD, it can be used for several different fields. Um, so um, I will talk about how we can access and what is the environment overview and how is it more user friendly. Like I keep saying, it is more user friendly. So access is same as other software like ETAP and Power Factory. I don't think Power Factory has a free version, but PSCAD offers you a free version, which can be used for up to 15 nodes, which is not huge, but at least you can play with some circuits. So and get used to of different components in the software. You can actually open larger systems as well in free version. It's only that it won't simulate those models, but it still gives you this um, facility that you can have a look at the models and play with different components, build circuits as large as you want, but just you can't model or you can't simulate them. So there are educational version as well, and they can go up to 200 nodes, and obviously if professional version goes to unlimited nodes. So unlike other power system software, paid version has unlimited nodes. So you don't have to worry about the number of buses or other things. So PSCAD actually stands for Power System Computer Aided Design, and EMTDC is called Electromagnetic Transient in DC System. So this algorithm was actually originally developed by Dr. Dennis Woodford from Manitoba, the University of Manitoba in Canada. It was developed actually in late 70s. But it doesn't mean that it can only be used for DC system. Like I said, it is very, very useful for AC systems as well. So flexible AC transmission system. So you can do everything with the AC systems, from low voltage DC to high voltage DC, HVDC transmission lines, And similarly, AC, transients, fault and protections, transformer saturations, wind power, power quality analysis, and voltage right through, frequency right through, all of those analysis you can do in PSCAD. So this is an environment overview. When you open the software, it gives you this overview where you have some examples and tutorials which you can look at. And this library, which is called master library. So it has several built-in modules which you can just copy and use to build up your model. So which is pretty much similar to Simulink. So when you use MATLAB Simulink, so you can just use already built-in modules. So which is what makes it much more user-friendly. So that's one thing I like about, like you can have not just components. It gives you the modules. So it means like fault logic and machine models. And you can actually find several machine models in that master library, which you can just copy and use in your system. So that saves us a lot of time and effort. The loading a project is simple. You just load the new project or examples. So another very good thing about PSCAD is they have a very well developed knowledge base. So if you go to their knowledge base, they give you a lot of examples and tutorials officially from PSCAD. You can have a look at different type of systems. They have all different types of systems, from steady state to dynamic, transient, and including wind power, solar power, battery storage systems, microgrid systems. So there are a lot of examples and tutorials. You can have a look and you can get started with those. And then building a basic project is just building a new case. And so this environment here is called workspace. So within one workspace, you can actually build multiple models. Same like Dixieland Power Factory. So you can have different case studies and build different models within one workspace without having to leave this workspace. You can do multiple things. And components, in terms of components, it has all the basic components in addition to those modules in the master library. And the measurements can be done directly. So similar to Simulink, you can use these measurement modules or measurement components like ammeters, voltmeters, multimeters. And so one very interesting thing with PSCAD is it uses signals instead of the physical connections. You can just use signal names, means you don't need to connect the two systems physically together by building lines and connecting them. So you can just give it an output signal from one system and then use the name in another system. So or another component. So then it saves a lot of efforts and makes it look a little bit more cleaner and tidier. So you don't need to have physical connection, so you can name signals and use the signals, and then you can plot those signals. So you can use those output channels, which can produce the outputs in real time. So you can, when you run your simulation, then you can see the outputs in real time. So these outputs can be added to graphs or charts, and then you can have a look at their basic overlays, and because sometimes when we are doing modeling, we are not sure what will be the output and whether it is acceptable or not. So if you're monitoring in real time, that the thing I like about it, that if you find something going wrong, you can stop there and go back, change your parameters, run it again. And it's like you can monitor it in real time without having to wait for the simulation to finish and then get your results and then go back and change parameters. So you can monitor in real time and then make your changes. So which I personally like, which is different from like ETAB or Power Factory. The time settings can be very, very small. It means you can use a very small step size up to like 50 or few microseconds. Because most of these EMT studies are time domain, so it gives us a lot of flexibility with time steps. So we can have a microseconds time step so that we can capture important information during those transient periods. And another very interesting thing with PSCAD is that it provides you these logical modules, like you can design a breaker logic and or a fault logic, and then you can tell it when to run. So instead of writing codes, I know it can be done with other software as well, like Power Factory or ETAB, that you can code or you can program it to do a scenario, right? But in this case, you just need to use a module, set your time, that's it. And then you can run the logic, breaker logic or fault logic according to that. So that can be very useful when we are doing dynamic studies. Obviously, we want to, during our simulation, we want to introduce some faults at certain time for certain duration, and then look at the behavior. And well, many times we also want to run it for multiple faults. So we can simulate multiple faults at multiple locations at different time intervals. So that gives us a lot of options, and so that we can test the system for different scenarios. So distributed transmission lines can be modeled. So just from the component wizard, we can build transmission lines. And then, as I said, we just need to like name the models, name the signals, and we can choose several different models from the master library and use those for our power systems. So PV systems, as I was saying, it is one of the most important component these days in our power systems. Everybody is trying to switch to renewable energy sources. So it has become an important component of power system studies. I mean, over the past few years, almost like 90% of the new power systems we have designed, they have some kind of renewable energy source, like a wind power or solar power or battery storage system. So then obviously converters and inverters are very important. And so for our power system studies, we need to be able to model them. So this PV inverter, which I'm going to discuss, is it's a generic Obviously, every manufacturer has their own design and own principle of operation for their inverters, but a generic PV system can be designed like this. Uh, if we go into detailed design, then obviously we need to look at the manufacturer's data and specification. So then, because we are talking about dynamic modeling, for steady state, it is fine that you can use one generic model for different systems. But when we do the dynamic modeling, obviously, it is very important to do it according to the specification from the manufacturer. So various regional markets segments may have different grid codes. So like in Australia, we have a different grid code as compared to Europe and US. So the manufacturers, when they make inverters for Australian market, so they make sure that it is compliant to Australian grid code. So grid code is the actually code of operation, how the PV inverter should operate in integration with the grid. So it's different for different markets. So obviously, and then even within the same market, the parameters can be different for different designs. Even sometimes you have the inverters from the same manufacturer, but different versions, they can also have slightly different way of operating. So when we do dynamic modeling, we need to be mindful of those small changes. They can cause big changes when they go into big systems. So that is why it is important. So that's another thing where PSCAD is, I think, very useful. So PSCAD allows for analysis of unbalanced faults as well, like single line to ground or line to line grounds, which distinguishes PSCAD from other similar software like PSSE is also very useful software, but it lacks that feature. So that's where PSCAD is mostly used for dynamic studies. So in terms of this PV inverter, so that's a basic structure of three-phase PV inverter. As you can see, we have a DC link, and it can be PV array or other DC sources of energy, and then we have our switching sequence. We have three-phase AC output. So basically, we just need to model that in order for the inversion process. So that's very simple. But when it goes into a power system, like a dynamic power system, grid connected PV system, so then there are a lot of other controls we need to have in our PV system, because we need to meet certain requirements from the grid code, obviously, and so those are called grid compliance requirements. Sometimes we have AMO compliance requirements for larger systems, obviously. So then in addition to these basic inversion control components, like here we just have IGBTs and DC source and inductors and some kind of driver to control the PWM. But in terms of controlling the power quality, and then the disturbance control, the fault control, so we need to model several other control systems in our system, and which are mostly integrated when we buy an inverter, especially like for such a power system like grid connected power system. So mostly they have integrated control system within the inverter, but obviously for doing the dynamic modeling, we need to model those components as well so that we can capture exactly what is going on. So conventional power system, as you can see here, we have just a simplified equivalent circuit for our conventional power system where we have generator and grid connected, and we have a P point of interconnection. So this is relatively simple. So there's for an average model, right? So basically we use a two-bus system to illustrate real and reactive power for conventional generators. So we assume that this generator, which is producing this VPV, let's say this is bus 1, this is bus 2. So in a conventional power plant, we obviously have synchronous generators. So we mostly worried about certain parameters, like we need to control the output of the generator, then we need to control the voltage magnitude. So voltage magnitude is used to control the reactive power. So it means that the reactive current component, which is IQ, and by controlling the excitation, right? So by increasing the voltage, we can control the reactive current. So that is very simple. And similarly, the mechanical power is used to control the angle because it has moving parts. Unlike the modern generation sources like inverters, they don't have any moving part. So then they lack this inertia. So we can control the power angle in conventional generation sources. So the power angle of the output voltage that mostly corresponds to real current component of the, which is IP, obviously, so the output current will be IS, which is the voltage source current. So then we can control the angle by controlling the generator here. So that's a simplified, we call it two-bus system. So reactive power control is relatively simple. But in case of PV inverters, obviously, it is a little bit different. So to describe the relationship between this reactive power control and the voltage, so this equation can be used, so which corresponds, which shows the relationship of voltage at the two buses, so which is VPV and VS, and then the corresponding voltage drop across the reactance. So then we can measure what will be the reactive power losses in the transmission line, and conventional energy sources. So this can be shared. It can be either from bus 1 or bus 2, or it can be shared by both sides. So it means we can have this reactive power compensation. And also it can be compensated by these modern systems like VAR compensators or SVCs or StatComs, like I mentioned earlier. So equation which describes the relationship of voltage at two buses then can be written as in this form. So P is equal to VPV, Vs over X, S and sine of the angle. So that's very straightforward. So it is for this PVP simplified equivalent circuit. So all reactive power which is spent in the reactance. If it is supplied by the bus 1, so then obviously VPV has to be greater than VS, so that reactive power can flow from bus 1 to bus 2. And similarly, if the reactive power is spent in this XS reactance, so then VPV has to be lower than VS, so then the reactive power can flow the other way. So which is normally the case, right? So if it has to be shared, then obviously VPV has to be equal to VS in that case. So power converter based power system, as I said, it is a little bit different from the conventional power source. So in this case, the real power output can be increased in many different ways, not just by controlling the generator in like synchronous generator in conventional power source. So this can be implemented by increasing the real power output while maintaining the same condition like VPV is equal to VS. And so when it is an equal voltage condition, so both sides will share the reactive power loss in the line reactance. And when the IS increases, the power angle obviously increases as well. So, but we need to maintain the condition where VPV has to be equal to VS, right? So then the current needs to change, right? So it means the IQ will change. So this current IS is then decoupled into the real as well as the reactive components. So the real one is called IP and the reactive is IQ. So assuming that we have an infinite bus at VS, which is normally the case, which is the grid is considered as infinite bus. So the VS is constant, right? It means the impact of reactive power's contribution can be seen from this, right? So then the voltage equation is rewritten in form of this real and reactive current. So real current in this case is proportional to real power generated, and reactive current is proportional to reactive power generating. So if, for example, if we double the IQ here, right? So then it will double the voltage drop, right? So we will result in what? Which will result in increase in the VPV, right? Essentially, we are actually controlling the voltage by controlling the reactive current. So that is one type of control which we can use in these power converter based power systems by using the reactive current, and it inverters, because they are smart devices, so we can run those algorithms or controls which can control the reactive current injection and control the voltage accordingly. And so that's where they become as grid firming or grid forming inverters. So grid firming means they support the grid, and grid forming when the grid is lost. That's also called islanded mode operation. But these power systems have some limitations, obviously, because the two limits which are very obvious are that this resultant current has the maximum point, right? Because we use IGBTs for switching purposes, so they have a maximum current rating. So that this IS is limited because of the maximum current carrying capability. Similarly, the maximum terminal voltage, which is VPV, it's also limited because of the maximum voltage of power converter. So that's where we have these thresholds for our inverter-based systems. So when we do our dynamic modeling, we need to define those thresholds, like how much over voltage we can tolerate in our system and how much under voltage can be tolerated in our system. It can be different for different inverter manufacturers, but these regulatory bodies, they have their own set points, so they ask you to meet those requirements. So then you have to obviously choose those type of converters which can meet those requirements. So that's one of the criteria which we test when we do dynamic modeling. It's called LVRT and HVRT, means low voltage right through and high voltage right through. So for example, if voltage HVRT setting from AMO is the 1.15, means 115%. Similarly, under voltage is the 0.85. So it has to be able to tolerate that much voltage. So that inverter then obviously needs to meet those requirements, means that it has to be able to generate those currents if we need to maintain higher voltage. Similarly, if we need to maintain lower voltage, so then we can choose the converter accordingly, which can meet the requirements. So that's one of the tests we need to do with our converters. So so this is a phasor diagram again to show you the real and reactive power control in PV inverter. And so we can see the size of real current component. If we think it's increased to IP2, the size of reactive current component IQ1 can be maintained. So so then there will be an additional voltage drop, which will be due to this J access times IP2. So it will be proportional to those increase in that IP2 current. So this affects the increase in angle between VPV1 and VS. So because the size of the infinite bus is constant, so then the increase in IP increases the voltage drop. So, but it decreases the voltage VPV2. So then if the size of reactive current component stays same, then the resulting voltage drop, which is J-axis IQ2, also stays the same size. So that's just to show you how it operates with respect to these reactive and active real currents. So this is a model. It's an average model. So obviously, average model means overview of the model, how we model a current source inverter in PSCAD. So as you can see, we have a voltage source here, and then we have our converter here, which has a DC link, and then we have switching. So that's an average model. So if we go into details, then we can have a look at the switching sequence and mechanism, how they are working and what parameters are controlling the switching. And then we have our transmission line, and that can be used. So the PPV and QPV and similarly VPV are defined in this block. So somehow it shows the direction here, but it is this block, the converter block, where we define the PPV and QPV and VPV. So the equivalent model is the same as the two bus system which we discussed. So we can monitor different voltages and currents by using those signals. So VPV, IPV, so we can break them down into individual components for three-phase converter-based system. And then similarly, we use, so PLL is a very important component when we are modeling the PV system, grid-connected PV system, because it is used to define the reference frame for D-axis. So DQ transformation is very important for grid-connected system, because if we want to model the line side converter, so then obviously we need to be able to convert it into ABC coordinates. So this is just a line side converter, real and reactive power control, which is simple. So we have inputs which are the reference points, and then we have our monitoring points, so QPV and PPV. So that is a typical control system, feedback based control system. So where we have our PI controller and the transfer functions, so we can compare the set point or the reference point with the actual point, and then we can generate an error, and that forms our reference IPV. And then that signal can be used to control the output. So means we can control how it will behave in certain conditions. So means we can measure the voltages at the point of connection, and so those disturbances can be monitored at point of connection, and then we can send signals back to our converters to change the behavior in real time. So these are base parameters where we can set the base power generation, like how big the system is, and what are the requirement in terms of the reactive power. And similarly, we can model for the base voltage, so 33 kilowatt volt system or 22 kV or whatever our system is. So that can be just defined by base parameters. So as I said earlier, in this case, we don't really need to connect those different components all together. We just need to generate signals, and then we can use those signals as you saw in this previous slide. So we can use those signals here in any component. So once you have this signal name, you can then use it anywhere in any block of your power system. So this is the typical block. So it also provides you this modules for part transformation and Clark transformation, which we normally use for DQ transformation. So you can, for a line side converter, we need to convert from DQ to ABC, or similarly, we can convert from ABC to DQ. So that makes it very, very easy. So it means you can just use signals with those blocks and then convert them to any reference frame. That signal then can be used for other component. So this is just an illustration of this conversion. So you see in DQ, the first graph is the current reference in DQ format, and then we have it in ABC, so three-phase sine waves, which is typical ABC. So detailed model, as I said, that was average model. So we have this detail model. If you're going to detail model of the converters, obviously it needs to have these switches. Three-phase converter has 6 IGBTs, and then we have you can use your flywheel diodes. So, like I said, it depends upon the manufacturers. Obviously, the detail model is driven by the manufacturer specs. So then you can model it. So this just wanted to show you, you can model it to any specs, means you can do pretty much everything in the PSCAD to model it to meet the manufacturer specs. So this system here is called Smib model. So SMIB stands for small machine, single machine infinite bus system. So where the grid is modeled as infinite bus, and so we look at single machine. So that's called a Smib model. So power switching control, as I was saying, these switches obviously need to be controlled in response to what we are measuring here at the point of interconnection or anywhere. So these are the measurement devices. As you can see, we have multimeters measuring the current voltages at different points. So this type of comparators you can use in the PSCAD to define the control for the PWM. So if we need to change the switching sequence in response to certain disturbances or output, so that can be very easily done. So this is a voltage source inverter. So current source inverter is, I would say, probably the most widely used type of inverter, especially with these grid connected systems. So we use current source inverter model mostly, but we can model the voltage source inverters as well. And obviously in this case, you need to be able to control, you need to be able to provide this constant voltage source. So then the controls are, the detailed controls are a little bit different from the current source inverter. So which is also working on this feedback system. So instead of just monitoring the current, we are monitoring and controlling both current and voltage at the PV or the point of interconnection. So decoupled VQ control for line side converters. So again, we can convert these from one reference frame to another reference frame, and we can use it for our output, like we can plot the data, and or we can use it in another type of converter, like a synchronous generator. So similarly, we can control PWM for voltage source inverter as well, same like current source inverter. So power plant controller is another thing which we use mostly for larger systems. So when we have larger systems integrated with the grid, and then grid compliance, or say same like AMO compliance actually, they are a little bit complicated. So in order to meet those compliance requirements, we need to use a power plant controller on top of the inverter controller. So this power plant controller then obviously has several other parameters which it needs to monitor and control. So power control, Q control, current limit logic, and so it has several reference inputs. So here REPC. So this is a supervisory control, which is implemented to control the real and reactive power of an entire PV power plant. So inputs can be reference voltage, reference reactive power, reference real power, and frequency reference. So there's control block, then functions to control the real output to respond to a frequency disturbance and to respond to voltage regulation at a bus. So that's where when we simulate a frequency disturbance in the grid, and how does our inverter con control the response, because then same like voltage right through, it also has to have this frequency right through, frequency disturbance right through, where if frequency changes, for example, to 51 hertz for some time period, it needs to be able to maintain its operation, because if it doesn't, then it can cause even more problems for the grid. And then that's what we call avalanche effect. So if the grid has some frequency or voltage disturbance, and then the inverter shuts down in response to those disturbances, that can even more destabilize the grid. So that's why we need to use these controls or these kind of ride throughs, so that instead of being a burden on the grid, these systems can support the grid. So that's why when we're doing dynamic modeling, that's one of the key components we need to look at in our studies, that how does it respond to certain frequency disturbances. And AEMO has very clear guidelines in terms of frequency disturbance. If frequency changes to 51 hertz, your system needs to stay operational for certain time period. And similarly for voltage disturbance, like I said, if voltage goes above or under, then there are time limits. So your system needs to keep up its operation up to those time limits. So obviously if it goes for long, then it goes into this fault mode, and then obviously it can be a big problem. But for short time period, it needs to maintain its operations. For that, we need to have these kind of controls. So this RWCB, that's this power converter control, which is obviously implemented to limit the currents based on the current carrying capability of the power switches, so that we don't overload the switches or damage them. So different types of reactive power controls are implemented in this block as well. So like Q control and P control. And then in this REGC, this is a generator controller. So it is implemented to the grid interface, like under and over voltage scenarios. And then it enables non-linear current control capability, so that when there is disturbance in the grid, so then it can generate those non-linear currents, so then it can maintain its operation. So there are several other detailed components. Unfortunately, we don't have much time, and I want to show you quickly the software interface and the model, how it runs, and how it looks like in real. So there is a reactive power and voltage control. Again, we can use the reference signals to control these. And similarly, we can identify abnormal voltage ranges, because we can define the ranges. So V dip and V up, we can define within this controller module, so that it can identify if it goes up above that, so then it goes into fault mode. And so in between, it needs to have this, which is what we call dead band. So it has these voltage deadbands and similarly frequency deadbands. So dB1 for under voltage, dB2 for over voltage, and then even after that, it has this ramp rate. So that's ramp rate also defined by these regulatory bodies that it needs to have this ramp rate to shut down and or to ramp up the voltage. So that can also be defined in this model. So we can use this voltage control block to define dead bands and current limits. And we can also do real power control. Obviously, we can define ramp rates because then again, these regulatory bodies or network operators, they have requirements in terms of ramp rate because the renewable energy sources, they are very dynamic in terms of their performance. Also, like solar power system, it changes throughout the day. Means the irradiance from the sun changes throughout the day, and then when there is a cloud cover for like 5 minutes, it its output changes, and then it comes back to full output. So if we don't use those ramp rates, that's obviously a big fluctuation which the network has to bear. So that's where we have these ramp rate limitations. So then when there's a cloud cover, the output from the solar array goes to 50% or 20%. When it wants to come back, it can't just go directly to 100%. It has to ramp up slowly so that the network doesn't become destabilized. So yeah, there are several different, actually this dynamic modeling is so much detailed, so means and it's very, very interesting when you start doing it. So and then you can also have this priority operation where you want P priority or Q priority, means the active power priority. So we want just the active power control or the reactive power control. And most of the network operators, they ask you to do the power factor control. So it means where you are obliged to maintain the power factor. So then you can also define that one as well. So I had the example for the battery storage system as well. So with this buck converters and boost converters, but I think I can just quickly go to software. Can you guys hear me okay?
Yes, we can hear you okay.
Okay. I hope I'm not going over time.
No, that's all good. It's very interesting. Thank you.
Okay, so you can see the interface, this PSCAD interface.
Yes, we can see.
Yeah, so this is one of the system I've been working on. It's a large scale solar farm, and it has this grid connection. So we model this as a SMIB, again, small machine, single machine, infinite bus model. So as you can see, we have several different components in there. So first of all, we have our PV array. So PV array as it can be modeled. So PSCAD has a built-in module for PV array. We can just use it. And then we can control the operation of PV array by using these input signals. So it means we can change irradiation, temperature, and this can be automated. Means you can run it from like 0 to 1000 irradiance or temp. Similarly for temperature, because temperature derating is also one thing we need to keep in mind. And then as the battery storage, so this part here is the converter module for the batteries, and this switch module here is for as a is an inverter. So if you go into that, so you can see all that which I was showing you in the slide. So it has the switching sequence and different signals. Then we have the PWM control here in this part. And yeah, so then we have this cap bank for the capacitance along the line, and this PI section, as I was just saying. So in order to, so what this PSCAD does is it can centralize the capacitances and impedances of the line at one point. So means we can just use this pi section to define the impedance and admittance and reactance values for the line. Obviously, it depends upon the conductor or the length as well. And then we have this transformer. So typically we use Y delta transformer when we have our PV system integrated with grid. Obviously, that PV side is Y, and then the grid transmission line is delta system. So that can be also modeled. So then in terms of the dynamic studies, so these are the different components, like I showed you PLL. So this is phase locked loop controller, and that can be modeled. And similarly, we have this controllers, which I was discussing. So inverter control. So it has all these reference points, GRP1, GRP2, group 1, group 2. So we can actually group signals in this PSCAD. So instead of doing one by one, we can group. So if the inverter controller needs several, like tens of inputs from different points, we can group them here. So as you can see, this is like grouping of signals. We can group the signals and then just use the one signal as an input to wherever we want. So that makes it very convenient instead of like writing tens of signals. I just use one signal as an input, and it takes with it all of those signals. And then we can write. So what we do normally is we write library codes. So that's another very interesting feature with PSCAD. You can write library code. So as you can see here, so at the left hand side, you will see these. So all of these have, so we can write source code. So like we are sending inputs to this inverter control, but what happens inside the inverter control? So that for that you can write your source codes, which can be your proprietary codes. So that's where we can build libraries to protect our proprietary system. So but this can be done as a generic as well, like we looked at in the slides. That was the generic system. So, and then we can have outputs. So those outputs then can be used here anywhere to plot or use for further analysis. So this is a temperature control derating controller. So it means how the temperature affects the operation of the inverter system. So then that can be modeled as well. So this here, this large block is PPC, the power plant controller, which I was telling you about. So that in addition to PLL and inverter control, we need to use this type of power plant controller in like real systems. So that's what we need to model in here as well. So that can provide all those REPC, REEC, and REGC functionality. So if you go into that, you'll see a lot of different parameters. So you can define the dead bands and the gain for active reactive powers and the controls which you like. So again, this can be modeled. So we have modeled it as a source code. So you can use Python. So it uses Fortran compiler So different type of Fortran compilers can be used. Intel compiler and then G Fortran. They also have this compiler, so they can be used for compiling your system and running the simulation. And so this is another part where we can do those grid compliance studies, like the rate limiter, as you can see, rate limiters and ramp down, ramp up. So if you, this is a module, built-in module in PSCAD, it's a rate limiter where I can limit the voltage rise. So a maximum increase or maximum decrease rate for the voltage, as I was showing you in the slides, that um, once when there is a cloud cover, so voltage goes down from the PV source, and when the cloud goes away, it comes back. So going down and coming up, if it is sudden abrupt changes, that can immediately affect the grid or the network, right? So in, it's not just for the modeling purpose. In real systems also, they use this kind of ramp up, ramp down controls. And then we can use these timers, it's called range comparators, to simulate certain disturbances within the system. Um, so, and then we can have this kind of graphs and controls where we can plot in real time, like data in real time. So probably I can run one simulation for you. So this is a system, and this is timed fault logic. Then you can define to simulate faults at different times. So here I'm using just one. And then the fault logic as well. So you can simulate different type of faults. So you can use faults for different resistances, and then you can define different type of faults, like single phase to ground, or single phase or two phase fault, or three phase faults, or unbalanced faults. Like here we have line to ground faults. So you can also model this breaker. So breaker can also be modeled as a breaker logic. So that breaker can open at certain time and close at certain time. And then we have this RLC block where we can define the resistances and the inductances of the line and of the fault, sorry, and similarly capacitances. So that can be used. So what will be the, so depending upon the RLC value, it will control the residual voltage. For example, when there's a short circuit, what will be the residual voltage? So that can be exactly modeled by using this RLC block. So if I just run a simple calculation, so we can just run it. And here you can see these are called virtual lines. So it shows you where each signal is going. So just for an idea, you can also hide it if you don't like to see so many lines. I like to see, for fault finding, it's a very good tool. So you can use virtual lines to see what signal is having what problem. So another thing, when you run simulation, you can go to project and define your run times. Like I want to run it for 50 seconds, and the time step is 16.66 microseconds at also an IMO, sorry, AMO's requirement, and then the plots step is the step size between each. So when it compiles, so this whole thing is a compiler matches messages. So when it compiles, it starts running simulation. And I like to hide my graphs on a separate page because I like to make it neat and clean. But you can plot your graphs on here. I would like to build this kind of module, these graphs and controls modules. So if you go into there, you will see all your results coming up there. So you can see here, so I have this POC, means point of connection voltage, power at POC at the generator, and reactive power at generator and at the POC, and similarly frequency. So, and you can see that it is real time showing the results, what is happening with the system. So at the present, I didn't simulate any faults or disturbances. It's just doing the normal operation. And probably I can stop this one and show you how we can do a disturbance as well. So for example, if I want to do a fault logic, so let me, so this breaker is closed. So I want to simulate a 3-phase fault. Right, so ABC, so 3-phase fault, and then I say time to apply fault, mean I want to, when I start simulation after 5 seconds, start the fault. And so duration of fault, um, uh, actually AMO has certain requirements. So 2 seconds, they want to test the fault duration for 2 seconds, but it conflicts with the setting, which is for under voltage setting. So we have voltage protection settings. So if you see here, so for under voltage, we have a set point for 2 seconds. So instead of showing the ride through, because if we choose the fault for 2 seconds, the voltage drops below our under voltage protection setting. So then the whole system shuts down. So that's why I'm using 1.97 second for the duration of the fault. So if I now, so I just want to change the time. So probably if I now run the simulation, so we'll say it will model the fault at 5 seconds. So it takes some time to compile, but when you have like say repetitive tasks to do, like change the fault level and do it again. So what you can do is you can do this snapshot. So if I do snapshot now, next time I run the snapshot, it will start from this point onward, means it doesn't go into all that compilation thing. So that's one way to shorten the time duration. So you can see the time running here at the bottom. So we have set it up for 5 seconds. So when it goes to 5 seconds, so because we have our controller like voltage ride through, so hopefully it should ride through the fault and continue working without shutting down. Yeah, so in the meantime, if you have any questions, please feel free to ask.
In terms of scale, so what scale we are talking about? Like for this simulation, it is for a solar farm, or what is the
Yeah, this
scale
one I
of?
can show you the scale. This one is for solar farm. So these are different components. Sorry, I forgot to show you earlier. So those DQ transformations we were talking about. So we have the ABC, which is at point of connection. We are measuring through this multimeter. So that then sends those signals here. and then we do this FFT for your transformation and convert it into VPP 1, 2, 3 or other referenced signals, and that can also be used for converting it into line voltages or phase voltages. So in terms of the scale of the system, this one is for 5 megawatt farm, so 4.95 megawatt, and so actually this should be but yeah, it can be modeled for any size, just not just for that. So you just need to be mindful of your requirements of your system.
Sure.
As I said, this inverter, different manufacturers and different sizes, different versions, they have different specifications. So make sure you model according to the specifications.
So back then there was some changes in the regulations and there were some changes in the inverter standards. So how
Yep.
bigger of impact that was on the stakeholders and on the designer and system operators?
Yeah, actually there are changes every time. That's the one issue with this phase we are going through, you know, transformation. The regulations change very quickly from time to time. So in terms of impact, I think it was a big impact for the manufacturers because we heard because we have been designing and installing some of the systems when the regulations changed. So it's obviously then the manufacturers has major impact because they need to change their devices, their control system, and all those things. In terms of the modeling, yeah, it is also considerable impact because obviously when you have modeled, when you get used to of modeling one type of system, then if there is a change, then you need to understand what that change will cause and what modules you can use or how you can build up the model to reflect those changes in the specification.
Yeah, sure. Thank you. Anyone have another question?
So I just have a quick question related to the implementation of this simulation into hardware in the loop. Like, is it possible to translate these simulations into like, you know, hardware in the loop implementation, OpenRT or whatever is the other brands used in that? Is it straightforward? And if you have any idea on that?
So in terms of hardware implementation, you mean like in the real system?
I mean, in the labs. I mean, I'm talking from the academic background more than
Yep.
real implementation on the ground. Like, you know, that OpenRT and other tech, like other brands, they have the hardware in the loop implementation and all of that, which I believe PSCAD can be somehow converted into that implementation. So is that easy? Is it straightforward? Do you have any idea on that? And is there any other way to do that?
That's a very good question, actually. Yeah, I mean, for educational purposes or training purposes, that will be very useful. I'm not very sure, to be honest, how PSCAD implements that. I haven't done it myself, so I'm not very sure. Sorry.
That's fine. No worries. Thank you.
Yes. So yeah, this is what we were modeling for, so it's still going on. So because the time step is actually very small, it's microseconds. So it takes a little bit of time. Even if we said 15 seconds, but that is 15 seconds of modeling, not 15 seconds of modeling, but it considers those time steps as well. So it actually takes a lot longer than 15 seconds. The time domain it measures is for 15 seconds, but then the time steps make it longer. So as you can see that the power dip and similarly voltage dip when there was a fault, and the inverter system managed to ride through the fault instead of shutting down. So that's from the reactive power. So when it saw this fault at the point of connection, and it went into this reactive power control, so that controlled the inverter operation or the voltage and brought it back after the fault clearance, brought it back to normal. So then we can capture line voltages, fault logs, so we can give you the fault code as well. Means the inverter manufacturer, they have these fault codes. Means each fault code has a meaning. So this one here is obviously saying there's an under voltage. It is just in a type of alarm, flag. But when the fault is clear, the fault is clear, then this alarm also goes away. All right. So similarly, we can simulate for different scenarios for frequency disturbances. Like I said, we can model it to drop the frequency for a certain time period and then see how system behaves to those type of disturbances. We can model different types of faults. We can do multiple faults, and then we can do several other scenarios. So basic thing is how you build the model and representing the exact system, and then running those studies and capturing the data.
One question, Dr. Imtiaz. How did you do the initialization in your simulation?
Initialize, we just do this run. So you can run your model.
I mean, in Power Factor, at least we know that the initial value is coming from load flow, but as PSCAD doesn't have the load flow, so we need to give some initialization, which I believe maybe is not considered here. That's why if you look at, can you go to the plots, please?
To the plots.
Yes, and if we look at the reactive power, and before the fault happens, that time that it gets to steady state values. Oh, yeah, so you don't have initialization, so it starts from 0.
Yeah. We didn't consider that here.
Okay.
I just wanted to show you this fault ride through scenario. So obviously then, if we want to have some time for stabilization, so that's where normally we model it for longer time, and we can implement the fault somewhere after it has stabilized.
Yeah, I think if we do some initialization, then we can apply the fault, let's say at 2 seconds. Yeah, fair enough. Thank you.
Yeah. All right. So that's any other question from anyone else?
Yeah, if there are no other questions, I would thank Dr. Imtiaz for the detailed presentation on PSCAD. It was very helpful, and I have seen some of the tutorials on YouTube because they mostly just provide the schematics and don't provide the theory behind. I think this is very detailed and detailed in-depth, along with complex theory of and the principles are also very well explained in the presentation. Yeah,
Thank you.
we
Thank you.
really
I
appreciate
hope it
it.
was useful,
Yeah.
and I hope I didn't divert from the basic topic. Just
I know that was very helpful, and this is one of the most popular. We have maximum attendees. We have never seen this much attendance in any of our webinars. We really appreciate your time and effort
thank
on
you.
this. Yeah, thank you so much.
Yeah, I'm
Thank you.
very glad that you liked it. Thank you very much. Thank you, everyone. So, Dr. Adnan